So, last time we talked about Newton's first law, second law, third law, which forms the basis of what we call Newtonian mechanics, and I stated Newton's first law and talked about it in the sense that it defines a class of frames of references which we call inertial frames of reference. So, first law is basically related to identification of inertial frames of reference. If you have a reference frame, you have x, y, z axis given, you have clock given to measure time, and then you do dynamics of the particle here and there and look at the forces and look at the motion of the particle, you will find, if you have chosen inertial frame, then you will find that yes, if I do not apply any force or the net resultant force on a particle is 0, then the particle remains unaccelerated. If it is at rest, it remains at rest. If it is moving, it keeps moving with uniform velocity. So, these things we know from our schools, but the proper interpretation of Newton's law in this particular fashion, it is sometimes not done at a lower level. And once the inertial frame is defined, then comes Newton's second law, that in such frames, if you do apply a force, what happens, and that tells that yes, an acceleration will be produced. This is up to say first law, but then it is proportional to the acceleration, or it is product of mass and acceleration, or it is proportional to mass into acceleration, and the proportionality constant is taken as 1. We define units of force in that particular fashion. So, those things come after we have defined that inertial frame from the first law. And then the third law is that action reaction, which is really very difficult to practice, but then if you think in terms of forces, not force, forces, because you have two objects, one applies force on the second and the second also applies force on the first, they are equal and opposite, that is the weak form of Newton's third law, and then they are also along the line joining, that we call strong form of the Newton's third law. So, first let me talk of particle dynamics, that means I have just one particle and then there are forces on it, externally we are applying forces. So, dynamics of a particle. When I call particle, which particle or how big is the particle? We do not, generally we will not talk in terms of atomic or subatomic particles. Generally we will be talking of bigger particles, say at least micrometer type or millimeter type or centimeter type or meter type or kilometer type planets. So, those things we can do, but the particles means that now I am not interested in the inner structure of that particle. For me it is just one point, right. So, that is how we define our particle. It may be an extended body, but if all parts of the extended body move with the same velocity at particular instant, as time passes the velocity can change, the whole thing can be treated as a particle. So, it is not only just size, it is basically this, that if I am not interested in the internal structure, parts, how parts are moving or what parts are doing, I am not interested in that, then the whole thing can be treated as a particle. But you conceive this idea, you have a small particle and then we are doing dynamics of that. So, the basic equation is very simple, a force is equal to ma, and the stated problem of dynamics is that at a certain time you know the position of the particle, you know the velocity of the particle, and then as time passes you know at each instant what is the force on the particle, and then you have to predict that at a given later time where the particle will be and what will be its velocity. So, that is the problem. So, what is the problem? What is known at certain time, which we call t equal to 0. Remember, time has been flowing from time immortal and will keep flowing. So, if you say t equal to 0, you have chosen some instant and you are calling it t equal to 0. So, it is our definition of t equal to 0, right. So, in some questions if you get to negative value of t, that does not mean that it is unacceptable, it is unphysical. It is before that instant which you call t equal to 0. Before that also the motion was there, the particle was there, the forces were there and everything was there. So, if you are getting in some question, you solve it and you get t as negative, that does not mean that it is unphysical. It only tells that you have taken a particular instant as t equal to 0 and this result pertains to time before that. Okay. Nevertheless, at some instant which we call t equal to 0, position and velocity of the particle is known. That is one thing, and then the force acting on the particle is also known. The force may be same at all later instants, or force may depend on where the particle is. If the particle has reached from here to there, the force is different. If it has gone somewhere else, the force is different. So, force may be depending on the position of the particle, force may be depending on the velocity of the particle. If you throw something with high speed in air, the force by the air on that object, we generally call it resistance, air resistance, depends on the velocity, or the magnetic force depends on the velocity. Force may depend on the velocity, force may depend on time. So, whatever, but it is known, it is known. So, in that entire duration it is known. So, this is known, and what we wish to find, the position and velocity at all later times. To find, and this is known. So, that is basically the task of mechanics, at least when we do this particle dynamics, and the thing is very, very simple. You have F is equal to mass times acceleration. Remember, mass time acceleration is not the force, it is product of two quantities, mass of the particle and acceleration of the particle. This is equal to the force applied. F is equal to ma. So, this is force, this is not force. It has units of force, it has dimensions of force, but this is not force, this is product of mass and acceleration. Okay. So, and this is known, this is known. So, you have acceleration is F by m, mass of the particle is supposedly known. So, you write this as second derivative of position vector d2r dt square, that is equal to F by m. If you write in the component forms, Cartesian component forms, you have three equations, d2x dt square is equal to Fx by m, then d2y dt square is Fy by m, and d2z dt square is equal to Fz by m. You can also use other types of coordinate system other than Cartesian, then the equations will be different, but you will have three equations. So, this vector equation is a combination of three equations, and each of this Fx, Fy, Fz can be function of space point or function of time. or both. So, this may be some function of x y z, some function of x y z, some function of x y z, can also be time, but we will first deal with the forces which depend on the position of the particle. Just like if you have a pendulum, then whatever time, if the pendulum is here, you have a particular force, if pendulum is here, you have a particular force, pendulum is here, you have particular force. So, it depends on the space position and position of the particle, and therefore, it can be a function of x y z, it can be a function of x y z, this can be a function of x y z. If it so happens that it does not depend on x y z or t, it is constant, or during the entire motion of the particle we are interested in, this force is constant, then the life is very, very simple. d2x dt square is equal to a known function f x by m. This is constant, right? We start with constant force. So, this f x by m is constant. So, that is this, and then you can always integrate it. dx dt is equal to, this is one integration. So, f into t and plus some constant c1, and then again integrated, x is equal to half f t square and plus c1 t and plus c2, and this is the acceleration which is constant, which is known because it is f divided by m. So, if you write it as ax, this f x by m, if you write it ax, your x is equal to half a t square plus c1 t plus c2, and these two constants are not known as such with this much of information. So, what you need is at t equal to 0, that means at some instant I know the position and I know the velocity, and I am calling that as t equal to 0. So, what is known as x at time t equal to 0, that is known. I can call this position as x equal to 0. Okay. So, that is a standard way. If you say that this position I have chosen to be the origin, so here x is equal to 0, y equal to 0 and z is equal to 0. Just as you can choose a particular instant as t equal to 0, you can choose a particular space point as the origin, x equal to 0, y equal to 0, z is equal to 0. So, if you have chosen this particular position at t equal to 0 to be 0, you can put it here. What do you get? 0 is equal to t is equal to 0. So, this is 0, this is 0, c2. So, c2 is 0. So, you have x is equal to half a t square and plus c1 t. So, you get the value of one constant, but one constant still remains and one information still remains, because not only position, I also know the velocity, and velocity is here, velocity is here dx dt. So, at t equal to 0, if the velocity is known and if I call that velocity as u, small u, then what I get? If I use this, this is my Vx. So, if I use this information that at t equal to 0, at t equal to 0, the velocity or the x component of velocity at t equal to 0 is known, and I call it ux. Then I can use this equation, ux is equal to, and put t equal to 0, ux is equal to c1. So, if I put it here, this gives me ux is equal to c1. So, this c1 is that x component of the velocity at t equal to 0, and you put it here and you get your very well known equation, x is uxt plus half axt square, and same is the story for y and z components. So, uyt plus half ayt square and z is equal to uzt and plus half azt square. So, if you know the force and force happens to be same at all positions at all time. So, this is constant, this is ax, this is ay and this is az, and they are all known. then you can immediately write what is x, y, z at a later time t, and from here you can write what is so V x is equal to C1 is u x and this is a x. So, all those equations that you learned in the first chapter of your high school book in mechanics. So, all those things can be found from here. So, in principle the task is over, right, if it is constant. If it is not constant, then there are techniques. If you have this kind of equation, but then this depends on x or it depends on y, it depends on z or it depends on time, then you have techniques of integrations, and from there you will rederive the corresponding equations which will depend on how this f x, f y, f z are depending on x, y, z or time. So, those methods can be applied. Finally, you can get x, y, z, finally you can get v x, v y, v z. So, v x is this, v y is this and v z is this. Right. But we will be talking more about some parameters which are associated, like linear momentum, angular momentum, energy, which will be useful for our system of particles, which will be useful for rigid bodies, and which will also be useful in many cases for a single particle. So, let me talk about those quantities or those physical quantities. So, one very important parameter in Newtonian mechanics is linear momentum of the system you are studying. It may be a single particle or a system of particles, rigid body, whatever. Linear momentum. Linear momentum. To start with, I will be talking of a particle, single particle. I am talking of single particle system. So, linear momentum, and we define linear momentum as p is equal to mass times velocity. No fantasy, nothing special, this quantity is defined as linear momentum. It is by definition, this is the definition. This quantity is called linear momentum. Mass of the particle into velocity of the particle is called linear momentum of the particle. And then Newton's law, force on the particle is equal to mass of the particle into acceleration. So, this we can recast in terms of this. If I take dp dt, or from here also I can go, let us go from here. This is m into dv dt. Rate of change of velocity is acceleration, again by definition, right. There is no physics involved here. We define this rate of change of velocity as acceleration. So, it is this. If mass is constant, I can take it inside. So, it is d dt of mv, and mv is p. So, it is dp dt. So, force on a particle is equal to rate of change of momentum of the particle. Actually, Newton described second law in terms of rate of change of momentum only. The words used were in Principia were very different, but essentially the force and this rate of change of momentum, they are proportional. That is how Newton's started, and then from here we go to this F equal to ma. So, this is about force and P, and if this force is 0, force on the particle is 0, dp dt is 0, right, dp dt is 0, and that means P is constant, linear momentum is constant. Obvious, nothing to be derived mathematically. Obvious, if force is 0, there is no acceleration. If there is no acceleration, there is no change in velocity, and if there is no change in velocity and mass is anyway in Newtonian mechanics, we take the mass of the particle as constant, no change in P. So, P is constant. So, if a force is 0, then linear momentum is constant, and we will see that when we talk about system of particles or extended bodies which can rotate and other things, we will see that this translates to a very important law of physics which is called conservation of linear momentum. If the total external force on a system is 0, then the linear momentum of the entire system that remains constant. Is different from this. So far I am not talking of external internal forces. It is a one particle and I am absolutely not interested in what is going inside. So, any force on this is external. Okay. So, that is why I am not talking of any that word external force so far, but once you go to a system of particles where different parts of the system can exert forces on each other, then those forces are called internal forces, and any force which is coming from something other than this system, that will be external force. And conservation of linear momentum is essentially, if the external force on a system is 0, the total momentum of that system is constant, and if your system is just one particle and everything is external, all forces are external anyway if you call it a particle, then of course that same principle tells that if f is 0, then p is constant. So, that is about linear momentum, and we will be using this conservation of linear momentum extensively when we talk of system of particles, collision of two particles and all those things. Okay. The other concept is related to the force itself. Okay. If you have a force which depends on a space point x, y, z, force is a function of x, y, z. So, you have f, and that f is a function of space point. I am using Cartesian coordinates. If convenient, we can also use, depending on what problem is at hand, other coordinate systems, but let us describe our theory in terms of Cartesian coordinates. So, if a force depends on space point, then you think of this quantity. I have a point x, y, z. I have some frame of reference, some origin, some axis, some y axis, some z axis, and with reference to that I have a point x, y, z. Then nearby I take another point nearby, and this is x plus dx, y plus dy, z plus dz, and this vector I call dr vector or dl vector. Okay, we call it dl. People also call it dr vector. I can also take dr vector. And then this is a small line segment. So, we assume that the variation of x within this is infinitesimally small. That is how calculus works. Okay. If it is infinitesimal lengths, if this displacement is infinitesimal, if this dx, dy, dz are infinitesimals, then I need not worry whether force at this point, this point, this point, they vary. I am not worried about that, it is so small. So, whatever is the force here, I can take that as f, and this is dl. You construct this quantity f dot dl. And you can take a curve, you can take some curve. Let me take the curve somewhere here, and here is a point which is, we call it r1, this vector is r1, and another point we call this vector as r2. So, now I am going from here to here, big distance, not infinitesimal, big distance, I am going from here to here. I can add all these quantities f dl here, f dl here, f dl here, f dl here. This quantity I can add, take infinitesimal lengths and then construct this and add all that, and that will be f dot dl. From r1 to r2 along that path given, along the path given, because this dl I have to take this dl, then 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 this dl, this dl. If I take another path here from the same point r1 to r2, then I will be taking this dl, then this dl, then this dl, then this dl, then this dl, and so on. So, it is different, right, it is different. So, f dot dl along this path may or may not be equal to f dot dl along this path, okay. And this plays a very important role. Whether this integral depends only on these two positions or it also depends on the particular path I have taken, that distinguishes forces into categories. One we call conservative forces, other we call non-conservative forces. So, we will start from here next time.